So, good morning. Welcome to the Krishna's classroom. We continue with our discourses on ordinary differential equations. And what we did last time was to consider linear systems with the constant coefficients, the homogeneous linear systems, where we assumed the matrix A is diagonalizable. Okay, so that was the sort of simplicity that we sought. In fact, we have a very nice results regarding the diagonalizability and non-diagonalizability in all these cases, what one does and so on. Okay, right. So let us just briefly recall what happened. See, when it was diagonalizable, we got a basis, or what you call a fundamental system of solutions for the homogeneous equation, exploiting the diagonalizability. And this was possible. It is reasonably simple also. And there also two different situations arise. One, of course, all the eigenvalues are assumed to be real. There are many situations where it happens, like all symmetric matrices A, which is both diagonalizable as well as all the eigenvalues are real. Whereas more general scenario, the A is diagonalizable but having at least some complex eigenvalues. In that case, we found we can get real solutions or even get a basis consisting of real solutions once we get the complex valued solutions of the homogeneous equation. Now, this is fairly straightforward. Now, what we are going to consider is drop that restriction, namely A is diagonalizable. So, A is assumed that A this is the assumption. We are not putting any restriction, and you see that. Let us analyze the scenario. So, A is Aij belongs to R. So, the problem that you encounter is the following. So, we are considering the problem okay. What we do is we consider the problem in Cn. Now, in Cn, so if you look at this as, if we consider A as an element of linear transformation on Cn with C as the associated field. we have the characteristic polynomial of A splitting as the product of linear factors. Or you can write P lambda is of the form where because P is a real polynomial, polynomial with real coefficients. Now it has got complex roots, okay, and lambda I is not equal to lambda I whenever I is different from. This is the scenario that you have. The problem that you encounter is that if you take A minus lambda I, the null spaces do not span, put together do not span the C. Okay, so that's the problem, right? So that is the difficulty that one encounters. See, we cannot dimension of null space of is Ni, and of course here you have N1 that is there. So that with the eigenvectors, linearly independent eigenvectors, you cannot span the whole space. Now that's a difficulty. Okay. So this is a real problem that you have. In this case, what do you do? This is the question that you are asking. Now for that, we will make certain notations, and then I don't know whether I talked about the primitive solution. Yeah, okay, right. Then we had this, introduced this notation, d by dt equal to d, or put it this way, d denotes d by dt. Then if x is a solution, one, namely dxi by dt dx, then pd x is also one for any this we have seen already. This comes from if x is a solution. Now this is a consequence of the fact that xt is a solution of one implies now this we have observed or proved in the beginning, so that for any polynomial with real coefficients, now this we can assert. Now we have then proved the following theorem. Let suppose T naught belonging to T, some value T, xt naught is associated with a characteristic value lambda of A with multiplicity M that is equal to 0, then the same holds for all values of T that is A minus, oh this is the power n, A minus lambda I 0. Also d minus lambda to the power m variability. Now this is something which we have proved, and this result is very crucial. What it says is that if xt is a solution of 1, then for some value t naught of t, xt naught is associated with the characteristic value lambda of a with the multiplicity m, by which you mean that a minus lambda I to the power m x naught is equal to 0. Then you see that this relation is true for all values of t. I will put it here. xt naught is a fixed vector in Rn or Cn. Now let us quickly recall the proof of this. The proof of this is very simple, because what one does is the following. Okay. So what one does is the following. Yeah. Now you clearly see that a minus x t is identically equal to d minus this we know. This is true. And because x is a solution of that's the reason. Now we take or set equal to d minus lambda x, whatever be the function that you get. Then one observes that z is a solution of one, that is dx by dt equal to ax, and zt naught is equal to what? Zt naught equal to this is equal to a minus lambda I and this, you know, xt not being lambda where lambda a characteristic value of multiplicity, it simply follows that equal to 0. Therefore, X such that which implies equal to 0. Zt identically equal to 0 means what? That is d minus equal to 0 or xt is identically equal to 0, which is the same as a minus equal to 0. So this is the result that we have proved. Now we define things like what is called a primitive solution and so on. Okay. Let me just make some general remarks on how we handle this problem. See, A is now what you can do is we can write P lambda as that is what we have assumed. Now what one does, this is the characteristic equation. Therefore, if you just recall, see the minimal polynomial A is then something like this is the minimal polynomial for A. Let us write this by f where was 1 less than or equal to now what one can prove is this: the null space of to the power mi. The dimension of this is equal to ni. Therefore, what happens is that we take and we have and this is a direct sum. But we may not have, so if mi is equal to 1, then you see these are all eigenspaces, or what you call characteristic vectors. But otherwise this may not happen. I mean, that's the problem. Had they been just eigenspaces. Now you recall that A is diagonalizable if and only if, what do you have? Mi equal to 1 for so that may not be true. If it is diagonalizable, then we know how to work with it. But if it is not diagonalizable, now this is the scenario that you have. Okay. Therefore, let us work on this now. So what we want is, from this relation you see that you work on the null space of A minus lambda I to the power mi. So take one of them for a particular lambda and then try to work this out. Okay. So this is called the vector associated with lambda associated with a characteristic value of multiplicity m. Okay. So let us write down. In fact, see, the null space of this is the same as the null space of this. You can easily see. That's what the minimal polynomial comes upon. So let us write this one. So we write down definition. Primitive solution. A primitive solution where 1 is this one, associated with a characteristic value lambda of multiplicity m is any non-trivial vector solution of 1 for which lambda is a and m is a positive integer. Given by the multiplicity of lambda as a characteristic value such that a minus and d minus lambda equal to 0. Such a function x is what you call a primitive solution. Okay, so we will be exploiting these primitive solutions to construct a general solution of the problem. Okay, so let us work on this now. So the theorem that we have proved from the previous theorem, just put the remark. Proves that there exists a primitive solution. Xt is a primitive solution one if and only there exists some t naught for which xt naught is a vector associated with lambda with the characteristic value So associated with each of these lambdas, you can have primitive solutions. Okay. Provided you get hold of these vectors associated with each of these eigen values or characteristic values. Okay. Then all that you need is set up sufficiently many vectors which form a basis for Cn or Rn, depending on the nature of this. Okay. So what do we do? Okay. So how to get hold of these solutions? Now you see, what we know from the general theory is this. That is, this is the relation that we are looking at. Star implies there exists vectors associated with each of the lambda each of the lambda which span Cn. This is the advantage. Then of course you can get for Rn the corresponding real vectors you can construct. Now this we know. So you take one such vector. So okay. So let us start. How do we get the particular solution? Because you cannot work with eigenvectors in the general setup, we have to work with what are called the vectors associated with a characteristic value. Okay. So let us use this to construct the solutions. So theorem, how to get the solution from this. Now we use the previous theorem. Let xt be a primitive solution of 1 equation 1 associated with the characteristic value that is a minus lambda I equal to 0. Is of the form some P1T lambda t, where each PIT is a polynomial of degree This is what we prove. So once we prove this, then of course, so here we are saying it's not of degree equal to m minus 1, or it can take all possible values and then give you sufficiently many solutions. It spans the solution space. So let us work this out. This is not difficult. A very small thing that you observe, then it will give you the result. Okay. But this is a crucial step. By the previous theorem, what we have is that a minus lambda I to the power m xt is the same as d minus lambda so let then what you have is this. D minus lambda with T and I belonging to okay, so let us see what it leads to. So in general, the equation that we have to look at is this. Okay, so let us find out what xi's are, or try to integrate this equation. This is a differential equation of order m and xi, so we shall take a typical equation for any complex function with continuous derivative continuous derivatives, we have this relation d minus this is equal to sorry, I think e to the power equal to this. Okay, so we prove this identity first. Let's first prove this identity. Now this is trivial. Equal to 0. Okay. So what we do is now assume proceed by induction. By induction. So give an induction argument. Assume it is true for m equal to k minus 1. Then what do we have? D minus lambda Now let us work it out. We will compute this for d minus lambda to the power k this is equal to d minus lambda xt. And this part is actually d minus lambda, and we apply the induction assumption. So it says of e to the power lambda t xt. And now simply just evaluate this, and this you can show that this is equal to, and you can show that this is equal to e to the power lambda t into so that's what we want to prove now. It's okay, right? Now we can use this result. Now this is true for, if it is true for k minus 1, then it is true for k. Therefore we have the result proved, and we shall use this now. This the identity. Now we shall use this. Now we shall use this. How do we use this? So d minus lambda m, we write this e to the power lambda t minus lambda t into e to the power lambda t xit equal to 0. Okay. Or let me put it this way. Therefore, we will apply this result. If you apply this result, what do you get? Then this, if you apply for this function, then you are going to get then d to the power e to the power lambda t into d to the power m we have to work on this function. Okay. Equal to 0. Okay. Hence, we have that is mth derivative of e to the power minus lambda t which implies, now you can easily integrate this, which implies some PIT where degree of PI PIT polynomiality of therefore you have now the solution. The solution is equal to P1T e to the power so this proves the theorem. So we have got the structure of the solutions. Okay. Now the problem is we have to assert that a fundamental system of solutions of the equation 1 can be obtained, can be constructed out of this. So let me now the next result is we exploit this, a fundamental set of system of solutions of equation 1 of the system 1 of the form or you can even pull this out. Lambda t always exists. This is the first statement. So if all the characteristic values lambda I are known, this fundamental system may be constructed, obtained through a finite number of elementary operations. See, all this is supported by the fact that, see, you can construct a basis consisting of what are called the vectors associated with the eigenvalues of certain multiplicity. As I said in the beginning, that you have the characteristic equation which factors into linear factors, or characteristic equation linear factors into linear factors. Then you have got the minimal polynomial which again factors into the same linear factors with different multiplicity. And then you see that we have seen that you can construct a basis for Cn with the what are called the vectors associated with each of these eigenvalues of multiplicity that is indicated in the minimal polynomial. So you get sufficiently many vectors of this kind, linearly independent set of vectors. Corresponding to each one of them, you can construct the corresponding solution, and the solutions would look like this, where lambda turns out to be one of the eigenvalues. So that solves the problem completely. In fact, the special case that we have considered earlier is that we will be working with proper eigenvalues and eigenvectors in the special case where you see that all the minimal polynomial has linear factors and what you call k distinct linear factors. Okay, so that is then in that case it is diagonalizable, where all the eigenvalues that you get, or the basis that you construct, or the primitive solutions in those cases will turn out to be simply something, this part replaced by the eigenvector associated with the eigenvalue lambda of A. Okay, and that will form a basis. But we are now taking up the general scenario where that is not possible, and then you have to replace each one of these by a polynomial. So polynomial. That polynomial we will see how we are going to work with. Such a polynomial exists. So this is prove existence of is trivial. How do you get that? For there exists a linearly independent set of n vectors say xi naught of A associated with the characteristic values of A. The general theory is the one that supports all this. Now, define xit to be the solution of equation 1, that is dx by dt equal to ax, such that xi t naught equal to psi naught. These primitive functions, primitive solutions are linearly independent and is of the prescribed form lambda, where lambda is an eigenvalue or the characteristic value. Okay. So that is there. Now how do we proceed, actually craft these functions? So let us start working on this, the details of this. Okay, so let be the distinct eigenvalues. with the multiplicities. Okay, which means the characteristic, so you have sorry. So for any lambda, among them with multiplicity m, we shall choose we shall identify polynomials such that xt is a solution of one. So what do we get? So xt is of the form where Eij's are polynomials of ith order with undeterminate coefficients not n minus 1, this is n minus 1. So what you have is the solutions are of this form, with each one of this is a polynomial of degree less than or equal to m minus 1. You have plenty of such polynomials with three coefficients now. So how do we proceed to get the required ones? What one does is the following. We go step by step, but it would terminate, the process would terminate with a finite number of steps. So there is nothing to worry about it, but one can do it. Okay, so how do we get that? This is done as follows. First we start with, so take so these are constants then py1, py2 etc. pin are 0 degree 0. That means the first stage it is going to be a vector of the form, that is it is going to be something of the form x1 x2 etc xn multiplied by e to the power lambda t. Okay, then substitute xn1. What you end up with will be a eigenvector if at all there is a solution. Okay, the exponents cancel out. This is what you have. This leads to a set of linear algebraic equations to determine the undetermined coefficients of PIs. So this system may or may have none or no solution or one solution or several solutions. Which are linearly independent. So that is starting with what you do is in the first stage you write these polynomials as just x1, x2 etc. some constants. Okay. So in the second stage then you substitute in the equation, equate coefficients on either side and then solve. Okay. Similarly you work with, now choose I equal to 1. Then we work with PIs as first degree polynomials. Again, substituting in one, determine the and determine the coefficients. So in this way we continue the process. Continuing the process until, if necessary, going up to -1. We can obtain sufficiently many how many solutions you can get? A set of m linearly independent solutions. So for each I we obtain a fundamental set of solutions for the solution space. This is the method by which you proceed. Now what I want to do is I want to just do a problem which will give insight to the working of this, and that would help you to compute the various things. Okay, let me take this particular example. So you take A to be the 3 by 3 matrix -1, 2, 2, -1, 2, 2, 0. Then you see that the characteristic polynomial is which is equal to minus so the characteristic values are 1 and 2. Each of multiplicity one and 2 respectively. Now the problem that you encounter here is that of course associated with 1 lambda equal to 1 of multiplicity 1 see these pi's are all now constants, so you see it's of the form, so what you have is this, you are taking xt equal to x1 e to the power t is a solution. Substitute and then substitute, so what you end up will be a minus I of equal to 0. And you will see, you substitute in this and do the work, then you end up with say one can choose x1 equal to 1, x2 equal to 0, x3 equal to 2. So xt is, let me call that x1 equal to 1, 0, 2 e to the power t. This is one solution. Now from 2 we have to construct the other solutions. Okay. So with 2, what do you have? From the general theory that we have a primitive solution associated with see the problem that you have is this, associated with 2, see you look at this space, null space of a minus 2i. The dimension of this is equal to 1. So you don't have enough eigenvalues to craft your what you call a basis for the vector space. That's the problem. Okay, so you will have to work with more general situation. So the primitive solution associated with 2 is of the form xt equal to these are polynomials of degree less than or equal to 1. Okay, so we start with begin with xt taken as, what is it? Of where ci's are constants. Or in short, what you are doing is you are taking P1 t equal to C1, P2 t equal to C2, P3 t equal to C3. They are polynomials of degree 0. Okay, so corresponding to PI's are polynomials of degree 0. Substitute. So yes. Then what you get? Then you will see that it's quite easy to, it's just finding out the eigenvalues. So we can choose C1 equal to 1, C2 equal to 1, so what is x2t? So we take x2t as 1, 1, 2 e to the power 2, e to the power 2. Okay, so we have x1 here, x2 here. Now how to get hold of x3? See, the problem that you have is this: when you substitute this, okay, you end up with the equation a minus 2y of x equal to 0. Then you see that this equation will have rank 2. When it has rank 2, the corresponding null space has only dimension 1. What is the consequence of that? You will get only one linearly independent vector which serves the purpose. So you don't get a second one. Had the rank of this been 1, then we would have gone to the diagonalizable scenario. In this case, it is not diagonalizable. Okay, so let us go to the next case. That means we are going to work with constructing the third solution. Okay. Assume something of this type: C1 naught C11t C2 naught these are polynomials of degree 1. Substitute per C1 naught Cij's are to be determined. Okay, so okay, Okay, this would lead to these equations, namely this leads to the following equations, that is 1 1 minus 1 2 0 2 2 2 I minus 2 of this is what you get. These equations. Okay. Now this would lead to the following. The solution would turn out to be eventually lead to xt equal to this will be the second set of solution for this problem. Okay, so you can choose this as your x3t. Okay, so you have x1, x2 and x3. This you can verify. This actually gives the solution. Try to work this out. Okay, so I think I'll stop here. So this is an exercise where you can put your hand on and get x1, x2, x3 which are linearly independent and forms a set of primitive solutions which will form a basis for the solution space. Okay, thank you very much. I'm not going to do the calculations here. Thank you.